Welcome to my video, friends. So this is the 8th episode of digital signal processing, and we'll be looking at the audio effects that we are using in our day-to-day real life, and we'll be seeing how to implement them in MATLAB and Simulink. And the effects that we'll be covering today is distortion in rock music that we'll be seeing, and wah filter used in electronic guitar, and then flanger, tremolo, delay, reverb. So flanger is nothing but the signal, the delayed version of the signal, where the delay is a sinusoidal variation. So we'll be seeing how the effect looks like in later part. And tremolo is nothing but amplitude modulation of the signal, but the modulating signal is a sinusoidal variation. So the message, the signal, the audio signal is modulated with a small message sine wave. It's not a message sine wave, it's a small sine wave with less frequency. So you will have some effect perceived because of the sine wave. And then delay is like a delayed version of the signal. Reverb is like when you are in a concert hall and when you speak you will be having an echo, so that is so called as reverberation, and we'll be looking that in MATLAB. So the first effect we'll be looking is flanger. So let me tell you what flanger is in a brief way. So you will have a signal output which is the input and delayed version of the input, where the delay is a sinusoidal variation, low frequency oscillation. Generally will take from 0 to 3 seconds and a frequency of 1 hertz. But then it depends on how variant you want the signal to be. So we'll be seeing in the MATLAB code. So here I have taken a sound from the input, which is read by y. Y is a numerical value of the sound, and fs is sampling frequency, and the sound is read by audio read. Whenever you do mp3, you will have two matrices, two columns of sound signal. So I'm taking just one columns. So we'll see how the sound looks, how the sound is in the first. So this is the sound that we'll be crossing on this sound. So this is a flanger, as I said. um, so we are having a maximum delay of 3 milliseconds, which is 0.03, and we want the frequency to be 1 hertz. So we are creating a sine wave 2 pi into that frequency, and then we'll be giving the value of n, so that the sine wave ranges from -1 to +1. Then what we are doing here is we are doing what is the maximum delay that I can provide. Like if I have 0.03 as my maximum time delay, how many samples I can go back and forth if I have a frequency fs. So that's why I have written max time delay into fs. That will give maximum sample delay. So then the output. So out here the final equation will be the amplitude, some gain times 2 input plus input minus current delay. So what should be my delay? As if my current delay is greater than I, then the array index becomes negative. So it becomes an error. So that's why I am copying all the values till the maximum delay it can provide, such that array won't go into negative values. So then I'm looping it for all the values, and then I'm putting the value of delay, so that everything is processed. So it is just a feed forward method, not feed backward. So output is so this basically an FIR filter. So then I'll be plotting the spectrogram of output, input, and their time plots. So let me run the code. So flanger, as the output is like 68, 6,88,000 and 68, 86, 128 samples. So it takes time to process. So this is our output signal, and this is our input signal. And let's see what happened. Let's see the how. Here you can see the value is greater than 1, but here the value is less than 1, and something has happened over here. Let's see what has happened, and we'll be processing it. As you can see, the number of 0 dB and the number of maximum value uh, is more over here. You can see the change in the colors over here. This is like small blue, but this is like, I mean, light blue. This is like more area with darker blues. So there has happened some frequency changes. So let's hear what is the difference between these two songs. So this is the input sound. And we'll be playing the output one. So here you can see something is playing twice because of the delay. So I will again play the sound. This is the input. So there is only one signal going on. As you can see, at different frequencies. But when you play this process the signal, you are hearing something twice the what we hear in a CS. I mean, when played. So this is the flanger, where the delay is varied with respect to some sinusoidal signal. Then the next effect that we'll be going through is so called as overdrive. So overdrive is basically clipping of the signal. So we are having an non-linear characterization. So the output is a non-linear function of the input, and when the output goes beyond this value, the input is saturated. So that's what we are doing here. When the output is beyond this value, we'll be saturating the input. So we'll be having some distortion. The distortion, one type of distortion is so called as overdrive. So we'll be looking what the overdrive and how it is implemented. So basically the whole code implements the nonlinear characterization. So when the absolute of xi, because we are implementing in both plus and minus from 0. So when absolute of I is less than the threshold, here I am giving threshold as 0.33. So I need a 2 times x. And when it is greater than 1 by 3 and less than 2 by 3, so I want it to be a nonlinear function joining 2x and 1 within this range. So that's why I have written like this, as seen in the formula. And then when x is greater than 2 by 3, I want it to be saturated to plus and minus 1 accordingly. So I'll be plotting the overdrive. So here I don't require two sounds. So overdrive, let's first get the sound and then we'll hear what has happened. We know that what is the original sound, and we'll be hearing how the new sound new sound is. Okay, as you can see, there is a small distortion going on here, but it's not clear. We'll make it a bit clearer by doing. So we'll again hear the sound. Here you can see the distortion. You can see this clear. We'll plot the So here you can see this is the output signal from -1 to +1. As we are given the input 2 times of y. See, input varies from 2 to 2, and it has many distortions over here. It is like they are not at the same level, but our output is at the same level. So that's why we are able to hear the distortion, like they are in the same level of these values. So we are able to hear the distortion because of this, and this is a non-linear function. So we will again play the sound. Because of distortion. So this is a simple model of making a nonlinear transfer function for input and output. The next effect we'll be looking is tremolo. Tremolo is nothing but amplitude modulation of a signal. So tremolo, so the tremolo here I'm just having gain factor and the modulating message. It's not a message actually, it's a sinusoidal signal with the given audio frequencies. So our output is like amplitude modulated signal. So we'll see. I'm again sending a tremolo. So it's processing, and once done we'll be able to see what has actually changed over here. So let me plot sound. So you can actually see some other frequencies coming into pictures, right? So it's like something else is happening at that frequency, which becomes clear in the this thing. So here you can see there are less blues over here than the blues over here. So
కమ్మని ఈ ప్రేమ లేఖని రాసింది ప్రియతమా ఈ వచట కుశలమా నీ నిజట కుశలమే ఊహలేని పాటలే కనుల తోటలో తొలి కలల కవితలే మాట మాటలో ఓహో కమ్మని ఈ ప్రేమ లేఖనే రాసింది హృదయమే ప్రియతమా నీ వచట కుశలమా నీ నిజట కుశలమే గుండెల్లో గాయమేదో చలంగా మానిపోయి మాయ చేసే అమాయే ప్రేమాయే ఎంత గాయమైన గాని నా మేనికేమి గాడు నీవు సోకి సోకు కండేనే.
So this is what happens in tremolo, and then wah. This is one of the most widely used filter in guitarists and all those things. So wah filter, like you must have heard about the wah pedal that guitarists used. So here they'll be changing the output frequencies as they'll be changing the bandwidth and the center frequency of the band pass filter. So we'll be seeing what the wah filter in a brief way. So this is the input signal directly going, and we'll be having a time variation of the input signal mixed with the input signal. So this is the basic understanding of band pass. Band pass is made from high pass and low pass. So the center frequency is root over the frequency of high pass and low pass, and as once we change any of these frequency, our center frequency changes. So this is what the wah filter is, and we will see how the sound varies with respect to a wah. So here you can actually hear the difference of this filter with respect to that. You can hear the sound more distinct and clear with respect to the original sound. Here I am changing the frequency from 500 to 3000 with 2000. I mean, I want 2000 times the frequency to change in 1 second. So I am having a 2000. So what should be my delta from 500 to 3000? What should my delta if I want 2000 steps to happen? So delta is like fw by fs. So here I am changing the center frequency as a triangular wave. It keeps going as a triangular wave for throughout the input until it reaches the x. So f is something around f seen is something around, let's say like 2000, but length of x is like this much values. So what we'll do here is, until this value reaches the value of ax, we'll be making a triangular wave. So once the triangular center frequency is made, then we'll be making this filter. This filter is already predefined. So let's see how the filter looks. So this is the block diagram of the WAV filter, and it is created from many calculations from analog domain, and it is converted to digital domain. So the same frequency, the same block diagram was implemented in this one. So here, like as I said, just to avoid this negative array index, like we are calling the values from for one, and then we are processing for all other frequencies, then we are plotting it. So let's hear how the var looks here sounds like. So you can actually see like something else is added to the signal, right? So this is not the original signal. Our original signal was something like this, but our processor signal is completely different. So this is the var filter. So let's see like how to implement the var in Simulink. So let's open Simulink, and then flanger and reverberation. So I already told flanger is something where the delay is a sinusoidal variation. So the input is going with this is for no delay, so that the output is just the input song, and then this is the signal generator. And then when using the flanger, so we'll be having a sinusoidal oscillator, and then a sinusoidal varies from minus to plus, so we'll be adding one. It's up to us whether to add one or not, but it's better to add one, because if we don't add one here, we have to shift the song until it goes for maximum delay. So as we are not doing that over here, we'll be adding it one such that it varies from 0 to plus 2, and then we'll be um, gaining increasing the amplitude, as we are having 44,100 per once again. So we'll be increasing the amplitude such that it will have some 500 to 1000 0 to 1000 sample variation, or plus 500 to minus 500 sample variation. As 44,100 sample and 500 to minus 500, it doesn't make much difference, but you can see a small variation. So then giving it to the block of delay with a manual switch, so that I can switch between the original song and then modulated song. So this is basically the every block is self-explanatory, and here I'm using the encoder to make it a digitized form, sample and hold encoder. This is so this sinusoidal is analogous nature, but I need a integer value over here. So I'll be making a integer value by using an encoder where I have filled my sample should be somewhere around 0 to 500. Boundary point is 0 to 1000. So click OK. So it varies from 0 to 1000. And so let's hear how the output looks like. Let's run it. So as you can see, because there is a 1000, there is a 1000 degree I mean 1000 samples variation. So let's make it to say 36 or 100 or any value less than that, and let's again hear it. So here you can see the changes in the sound because of the delay. So let's again change it to 36, and we'll again proceed. It is just to make these songs visible. So as you can see here, like there are some distortion, but when you play the original song, It starts from before, and there is no distortion, no nothing over here. Everything is like smooth and so because of using this delay, like we are having a bit rough noise, the rough sound. But then when used in a proper place, like we'll be having this flanger effect. Then we'll be looking into reverberation. Reverberation is nothing but the when you are in a concert hall, you'll be hearing the echo or something like that. It is so called as reverberation. So you will have the signal and the delayed version of the signal. Then you will have the output as a feedback with the time delayed version, and it should have the gain less than 1, else the output will rise to infinity. And then it is given to saturation block. It is like whenever the input goes below minus zero point 0.5, it saturates to minus zero point 0.5, and above minus zero point 0.5 saturates to zero point 0.5, and then between these values it's a linear mapping. So we'll be hearing how the input looks. Input here.
The discrete Fourier transform of a real-valued signal is conjugate symmetric.
So this is the input of a sound speech signal, and then we'll be processing with the reverberation. So what if he actually talks from a concert hall?
The discrete Fourier transform of a real-valued signal is conjugate
So
symmetric.
here you can see
The
as if
discrete
he is
Fourier
talking
transform
in a concert hall. So this is so called as reverberation. Reverberation consists of the feedback as well as the delay or echo. So this is the reverberation sound of the input signal. So here we have seen many effects. Um, Delay, reverberation, tremolo. Tremolo is a amplitude modulation, as I told. Then flanger, wah pedal, distortion, overdrive. There are still many more effects that we can make. So the next video, like we'll be making about other effects that we'll be looking into it. And this was taken a reference from uh, in Jadavpur University by Ochisama Das. So I hope you enjoyed my video. Thanks a lot.